So today we will discuss, we'll start diffusion models. So the last class we did variational autoencoders, VAE. And we have seen that it's a latent variable model. And the basic idea in this is that we have an encoder-decoder form where the sample goes in and then it produces some output Z, and then we try to kind of recreate the vector X by using a neural network again, and then we use a so-called reparameterization trick where we kind of, if we produce mu theta, so basically what we produce here is mu theta and sigma theta square, which are the parameters for the normal distribution. And then we use a reparameterization trick. So if this is our Z, then we use a reparameterization trick where Z can be written as mu theta plus sigma theta epsilon, where epsilon comes from standard normal. So this is what we did in the last class, and diffusion models are a way to generalize this this idea. So basically in diffusion models we will see that it's a kind of a recursive variational autoencoder where we apply this repeatedly. Okay, but obviously there are some nuances that we will try to see. So as a next step would be something called hierarchical VAE, hierarchical variational autoencoder. So as I said, we will try to generalize this. So generalize VAE to multiple hierarchies over latent variables. And so here, as we said, we are generalizing VAE to multiple hierarchies over latent variables. So basically there will be multiple latent variables here. So latent variables themselves are generated from other higher level more abstract latents. So we can consider this as a most generic form of the hierarchy is when we allow each of the latent variable to be conditioned on all previous ones. So ZT is conditioned on all previous ZT minus 1, ZT minus 2, and so on. So that's like the most generic form. So a most general HVAE is with T hierarchy labels, and each latent is allowed to condition on all previous latents. Okay, so this is something we will try to kind of make it more precise. So what we want to do, we have seen VAE, and then we want to generalize VAE to multiple hierarchies. And here multiple hierarchies means that we will introduce many latent variables. Okay, so earlier here you had only one latent variable. So this is your Z, this is your X, and this is the model, the graphical model for VAE. And then going towards diffusion model, what we want is that we want to build on the VAE, and we want to create a hierarchical VAE. So here in this case, then we may think of X, then Z1, Z2, and so on, ZT. Okay, so this is what we are thinking of when we are saying hierarchical VAE. Okay, so in the third point that I have mentioned, it says that a very generic one will be to say that Z1 does not only condition on Z2, but it also conditions on Z3, it also conditions on Z4, and so on. Okay, and similarly X we can say also condition from Z to Z3. So this should be the very generic form of hierarchical VAE, but also it will be a very complicated one. So that's where we are saying each latent is allowed to condition on all previous latents. Okay, so this is pretty tough requirement you can think of, right? So because when we were developing models on this, then you will have many conditionals to handle. So and something similar you can think of as in RNN, I guess. Okay, so in RNN networks you have these so you have this X0, then X1 as input, and you have some MLP, okay, parameterized by some theta and so on, and then you have some output Y1, Y2. So here again it's like we have the weights across the latent variable, and then we have weights across these latent variables and so on. So here also in RNN we could have thought of kind of having multiple dependencies. Okay, and similarly here it also fits into here and so on. So we can do that, but it's just that the network becomes complicated. Here also we can do that, but again it will be a bit complicated. So what do we usually we will do is something called Markovian assumptions. So Markov assumption means that the current data is dependent only on the immediate previous data. Okay, so hence we will look into Markovian. So we will make this hierarchy that we are talking about. This hierarchy is Markovian. Okay, so assume the hierarchy to be Markovian. Okay, so then as I said, then it means that the current one depends on the previous one. So meaning decoding each latent ZT only conditions on previous latent ZT plus 1. Okay, so each latent ZT depends only on the previous, which is ZT plus 1, not on the ZT plus 3. or so on. Okay, so that's the standard Markovian assumptions you have. Okay, so okay, so we have this idea. We have VAE. We are planning to make it hierarchical. Now VAE was just this guy. We are planning to make it hierarchical like this guy. But when making hierarchy, then we may have a lot of dependence. Here was dependence on Z. Then we said that okay, this conditioning everything will be very cumbersome for us. So let us make it Markovian. So in this Markovian assumption, then we have X only dependent on this, Z1, Z2, and so on. So dependence is only from the previous latent. So this is our Markovian HVAE, we can say that. Okay, so we are using this word hierarchical VAE, and we can call this Markovian HVAE, or another name could be recursive VAE. That's also sounds good, recursive. Okay, basically we are applying VAE recursively. So we can make a proper diagram here. So let me do this diagram here. X, Z1, Z2, and ZT, and this goes like this, this goes like this, and this goes like this, this goes like this, like this, just like this. Okay, so okay, and now you can say what is this back arrow, right? So far I'm talking about this way, but remember in VAE we did had something back as well, right? So X went to Z, and Z we were trying to recreate X. So this small cycle in this case will also be kind of inherited here also. So there will be one forward pass, and then there will be one backward pass. Okay, it's just that now it will be done over T steps. Okay, so and in probability notations we can write these arrows, right? This is like Z1 given X, and we can use this as a Q, let us say, and this is Q of Z2 given Z1, and this is Q of ZT given ZT minus 1. Okay, and we can also say this for the reverse process, which is X given Z1, and this is Z1 given Z2, and so on. This is ZT minus 1 given ZT. Okay, so this is our notation, which is just extended from here. So now if we look into this as a graphical model, by graphical model we mean one at a time. So if I see it as a forward process, then it's a one graphical model, it's a directed acyclic graph. And if I see purely as a backward process, then it's also a graphical model that goes from here to here. So with this model we can compute the joint probabilities. So let us look into the joint probabilities now. So we can compute X, Z, 1 to T as, so we know the way to compute the joint probabilities using the graphical models. Basically, if you recall, then the probability of x1, x2, xn is given as basically probability of xi given parent of xi, and this is the product equal 1 to d. Okay. So this is the joint probability. This is how we calculate joint probability in graphical models. And depending on where the edge is between xi and xj, it decides the parent and hence the conditional. So in this case, it's a simple one again. So we have x and then z1 to t. Okay. So we are looking for the p case. So p is like this. Okay. So for this, if we write down, it will be probability of zt, probability theta, x z1, and t equals to t p theta zt minus 1 zt. So as you can see, I have just applied this formula here. Okay. So this is the root. So it has no parents. So that's just parent probability of zt, and then yeah, we can think of this as p theta, and then we have like t minus 1 condition on zt. So that's the generic way it's written. Only the x term, that the last one, is just taken out, and the root one is taken out because it doesn't fit in this generic formula, zt minus 1 zt. So only the first and the last one is taken out from the product, which was this one. Okay. And the remaining way we keep it in this product form. Okay. So it's a, so basically this was nothing but, so probability of x z1 z2 zt is I can write this as probability of zt, probability of zt minus 1 zt, probability of zt minus 2 zt minus 1. Okay. So I hope you get the idea, like I'm just recalling this. So this is from the formula here. Okay. So we apply the same thing here to get this, and similarly we can do it for the reverse process. So reverse process will be, let us say reverse process is denoted by some q phi. This phi and theta for the moment doesn't matter, we just keep it. So q phi of z1 to t given x is q phi z1 given x, and then product of q phi zt given zt minus 1 and t equals 2 to t. Same way we have done the q phi, now it goes in a forward way. So x z1 z2 zt. Okay. So we can now call these equations some name, h v a e1 and h v a e2. So we have a framework now of having this extension of the variational autoencoder to the hierarchical form, and in the hierarchical form we have relaxed the condition that it depends on all the previous latents. So we have made it into a Markovian one. It just depends on the immediate previous one, and then we have written expressions for the joint distributions, and for the forward process as well as the backward process. And as you can see, it's very similar to what we have done in the VAE. It's a form of kind of stacked VAE. Okay. Okay. So now, as we have done before for the VAE, we went ahead, we knew how to compute the joint distribution here, and then later on we went ahead to compute the marginal, which is what we want in practice. So we want the marginal p of x from the joint, and to do that we have to marginalize over all the z here. Okay, so the flow of the derivation is very similar to what we have what we have done before. Okay, in VAE, it's just that there are more intermediate determinant variables involved here. So we will go to, as I said, we will look into evidence lower bound, which is ELBO, evidence lower bound. And in evidence lower bound, like in VAE, we will look into log of p of x, and as I said, we will marginalize over the latent variables. So this is log of p of x. This is log of p of x given x joint with z1 to t dz1 to t. Okay, so as you have seen here, I am trying to marginalize the joint, okay, to get the probability of the px. So hence I have to integrate over all of the z. Okay, so this is what this step means. Compute by marginalizing over z1 to t. And if you can recall the VAE, the next step in VAE was something called importance sampling, because as in VAE case, integrating this is not tractable because it's integration over the latents. So hence we have to do some form of importance sampling that we did in VAE and create some lower bound of this, which we can compute. So the next step is importance sampling. So we will multiply and divide by a same quantity. So this is px z1 to t q phi z1 to t x divided by q phi z1 to t given x, and this is dz1 to t. So what I have done here, I have multiplied by this quantity q phi and q phi. Okay, so here q phi z1 to t given x divided by q phi z1 to t given x. Okay, that's what I have done, and that's also inspired from importance sampling. So what this does is that with this I can see these as an expectation over q phi. Okay, that's the whole reason, similar to VAE. So now I can replace this integral as log of expectation of q phi z1 to t given x and p of x z1 to t divided by q phi z1 to t given x. So what we have done is that this integral is nothing but expectation of q phi z1 to t of this quantity. Okay, so this is just definition of expectation. Okay. And then it's going very similar to what we have done in VAE, and the next step is computing a lower bound using Jensen's inequality. Okay. So basically log is a concave function, so log of the average, okay, and then so it's f of average. Okay. So in the usual convex function, f of the average is less than equal to average of the f. Okay. So basically f of expectation is less than equal to expectation of the f, right. So but then this is a concave function, so the same inequality changes. Okay. So that's for the convex. Now since log is a concave function, it's other way around, so the same inequality gets reversed. So now it will be average of the f, this is like f of the average will be less than equal to average of the f. Okay. So this will be I mean in the concave we just first we flip this, okay, otherwise is greater than equal to expectation of the f. Okay. So we have this form, right, f of the average is greater than equal to average of the f. So this will be kind of greater than equal to expectation of the log. Okay. So that's what we are going to do. So this is greater than equal to expectation of q phi z 1 to t given x and log of p x z 1 to t divided by q phi z 1 to t given x. So this is where we have applied Jensen's inequality. So most of the processes until here are pretty similar to what we have done in VAE. Now it's a matter of now substituting the probability of the joint with the P and then the Q that we have written there as HVAE1 and HVAE2. So that's what we are going to do as a next step. So plugging in HVAE1 and HVAE2, so in this last equation basically we can also name this as HVAE3. We might need this HVAE3. Okay. So plugging this into HVAE3, so what we have after plugging in is expectation of q phi z 1 to t x and then log of p zt p theta x given z1 product of t equals 2 to t p theta z t minus 1 given zt, and this is divided by q phi z1 given x product of t equals 2 to t q phi zt given zt minus 1. Okay, and we close this parenthesis. So what we have done is that we have just substituted HVAE1, basically this expression, and then the expressions for the q phi. We can have a quick look that everything is done correctly. Zt p theta x given z1 p theta zt minus 1, right. Okay, so we have just substituted that. Okay, so next we move to, so this is our basic framework, and we have to do some work here to make quite a few things tractable. So from hierarchical VAE, now we transition to something called variational diffusion model. Okay, so this is our elbow, the evidence lower bound, when we see things in a hierarchical form. Okay, and now how you will approximate these, okay, will lead you to variations in the methods. So let us look into something called variational diffusion models. So from hierarchical variational autoencoder and this formulation of the VAE, 2-3 papers proposed varying ideas based on this. So the reference one would be deep unsupervised learning using non-equilibrium thermodynamics. So this is by Dicksteins et al. And this was ICML 2015. So that's where they saw this idea of forward diffusion and backward diffusion. Okay, so they incorporate some physics idea there, but we don't have to go into those. So that's the idea behind these, that you have a forward process and then a backward process. There are a lot of detail there, so we will get there. But these are the early papers which we are trying to propose these ideas. And then there is something called denoising diffusion probabilistic model. So denoising diffusion models by Jonathan Ho in 2020 in NeurIPS. And then in 2021, like two years ago, we have variational diffusion models. And this is by Kingma and NeurIPS 2021. So they kind of simplify the ideas. Obviously, the papers they come later on improve a little bit, right? So they use something called signal to noise ratio form, and it kind of simplifies these methods. And yeah, we will get to that maybe in the next class. But today, I think the main ideas will be covered, and some variations of this will be seen later. Okay, so these are the key papers to read if you want to know. I mean, if you want to read the original author's paper, then you can read these. But essentially, we will cover the main ideas in our class. So the idea here is that we have left here until this form, which is the elbow for the hierarchical VAE, and the next step is more about like how do you go from here, right? So for instance, this is the picture that we have in mind all the time when we are discussing diffusion models. Like, what are the variations you can do here? Okay, so if I look into variational autoencoders, then z is much less in size than the x. Okay, so do you want to keep z shrinking as you go down? Like, what are the modeling things you have in mind, right? Should I shrink each time like VAE, and then I kind of enlarge it later on? So this could be another modeling question in itself. Second modeling question is, how do I model these problems going forward? So in the VAE, we had said that let us model this via some normal distribution. Okay, so here should we do the same thing, that I go from x to z1, I say that it fits some normal distribution, and then from z1 to z2 another normal distribution, and so on. Okay, so these are the modeling choices we have to think. Okay, so in VAE we did that. So both the encoder has this form where we wanted to produce a z which behaves like standard normal, and then we wanted to decode from standard normal via another normal distribution such that we could get back the original image x. So here again, these are the key things that we have to write down. So let us write down our modeling assumptions that we will assume, and to arrive at these diffusion models. So I will write down some of these key ideas. Modeling assumptions. So in modeling assumptions, we can say, okay, let us say A is, in the diffusion models, one of the modeling assumptions is, let us keep the z, the latent variables, same size as the x. Okay, so that's an interesting assumption, because in VAE we were trying to kind of give some advantages of having latent variables sizes small, because it can completely represent features and so on. But here we are saying no, we want z i's to be same as dimension as x, no compression. So that's the first thing that we will write down. So latent dimension is exactly equal to data dimension. Okay. Second one is a very also very drastic change, you can say, because first one is already drastic, that we want our latents to be same size as x. Okay, which is a very very different assumptions than VAE. And the second assumption says that the forward process that we will do, it will not be learned as such, it will be a sequence of, let's say, known transformations. Okay, so basically in VAE we were parameterizing the encoder via phi, and that phi was a neural network that was producing mu phi sigma phi. Okay, so this neural network was producing this too, which determines the normal distribution in VAE. Here we are saying that we won't parameterize the encoder, which is the forward process, this one. Okay, so that's also a very interesting assumption. Okay, so the structure of the latent encoder is not learned at each time step. It is predefined as linear Gaussian model. It is predefined as linear Gaussian model. Okay, so that's also a very drastic assumption we can think of. And then but we are saying that it's predefined, but we are not saying that it's the same transform, exactly the same transform. That's also we are not saying. So it is a transform, but we are saying, okay, the next time I will change the mean by some other amount, but that amount will be fixed in advance. Next time, so every time step, the linear transform, the transform may not be the same, but it's known. I know that at each time step what I'm going to do. Okay, so that's the third point. So the Gaussian parameters of the latent encoders vary over time in such a way that the distribution of the latent at final time step t is a standard Gaussian. Okay, so as you can see from the VAE point of view, we had this one layer and then we encoded and we were forcing these guys to be standard normal. So here also we are doing the same thing. There is no neural network involved here during encoding, just some fixed linear transform, and then still you want the jet t, the final jet t, to be some standard Gaussian. Okay. So these are the three modeling choices we have, and as it is fixed. It is not the same linear transform in each time step, but it is fixed one. I'm not saying the same linear transform you applied here will be applied here. It is a different one, but I know that for all time step, even starting from before starting this. Okay, so that's the point here. Okay, so these are the differences when you compare VAE with this. Okay, and obviously we are maintaining the Markov property. Markov property says that dependence is only on the previous one, immediate previous one. Okay, that's the definition of Markov property. Okay. So now let us look into the implications of these assumptions A, B, and C. Okay, so what does these imply? So, well, first thing that it implies basically is the notation we can, I mean, whether it implies or not, but first convenience that we think of is we can make all this to be x. Okay, so x0, x1, x2, x3. So that's the notation thing that we have. So, so implications of the assumptions. So the implication of the assumption A, this implies that so we can now represent both, can represent both true data samples and latent variables as xt, where x naught is true data sample and t lies between 1 to t, capital T time step, and xt is the corresponding latent width hierarchy indexed by T, obviously. So as a first step, what we have done is just simplified the notations basically. Represent zi's by also xi's. That's it. It's a simple notation thing. So as I have pointed out, the first of all, let us simplify these notations that we have, because now z is replaced by x. So with these notations, x1 to t x naught, okay, so basically z is replaced by x now. This is a simple thing. Okay, so very simple step here. There's nothing much to do. Now let us look into B. Structure of the latent encoder is not learned at this time step. It's predefined as a linear Gaussian model. Okay, so let us see the implication of B. So in this case, the distribution of each latent variable in the encoder is a Gaussian centered around its previous hierarchical latent. So we are trying to kind of expand on what we are trying to say here, but this is also not very clear, I know, like what is meaning of this centered around previous hierarchical latent, but we will make it very precise. So what it means is, like when we say that it's predefined as a linear Gaussian model, it essentially means that the mean and the variance is kind of made precise. Okay, when I go to the next, so I mean, these this mean and variance basically we have to change, okay, to get to the new Gaussian. So I think it's good to kind of precisely write down what it means. So what it means is that the mu at the time t, we want to see how it's related to the previous hierarchy, right? So mu t for xt is defined to be square root of alpha t xt minus 1, and this is our mean, and variance is defined to be sigma t xt is 1 minus alpha t identity. Okay, so we are saying that we are going from one Gaussian to the another. Then the only thing you will ask is, if I'm going to the next Gaussian, then what would be the mean? Then I say that take that as a mean, xt minus 1 you know, okay, and then you will say what is the variance. Then you take sigma t, and alpha t's are defined for you. Okay, so that's what it means. That's what it means. Like, what do we mean by defined advance? So these alpha t's are defined. Okay, so before even I start from the first time step, I have these alpha t's predefined, and these alpha t's help me transform from the previous Gaussian to the next Gaussian, and so on, by translating their means and the variance. Okay, and yeah, the how we choose this is something we will kind of see it at some point. So, but for the moment, we will just write down a line where we say that where we will make it more precise later on, but so here we will say where the form of coefficients alpha t are chosen such that the variance of the latent variables stay at a similar scale. Stay at a similar scale. Okay, so I'm not making it very precise right now. So these alpha t's will be chosen in a way that variance, when I go from one to the next, remains at a similar scale. In other words, what we are asking for, this is the encoding process. Okay, so in other words, the encoding process is variance preserving. Okay, so and we can have alternate parameterization as well, like this is one of the possibilities, right? Now how you do this parameterization depends, and you may discover new methods by changing this parameterization. Okay, so alternate parameterizations exist. Okay, so I won't say too much right now. We will take this parameterization for the moment. Okay, so with this we can kind of say what would be our distribution with these parameterizations and the fact that they are Gaussians. So this will be written as normal xt and then square root of alpha t x t minus 1 minus alpha t. Okay, so that's what it will be. I have a new normal distribution whose sample is given by xt and then the mean is given by square root alpha t xt minus 1. So this gives the new mean for xt and then the new variance for xt. Okay, so that's the form of q in the successive forward pass. Okay, so now we look into implication C. Okay, so what does C imply? Saying that the Gaussian parameters of the latent variable vary over time in such a way that the distribution of the latent at the final time step t is the standard Gaussian. Okay, so what we are expecting is that via this process that we are doing, we will reach a stage where t will be capital T, and then we expect that this guy becomes 0, 1. Okay, it becomes a standard normal distribution with mean 0 and variance 1. Okay, so in other words, the way you choose these coefficients alpha, it should be such that you get a purely standard normal distribution. Okay, so choice of alpha t is going to be important. Okay, and so that's the expectation, and then there is a reverse process where we go from standard normal back to the original image. So this is what this C is trying to indicate, that whatever transformations you are doing, it should be such that the final xt looks like standard normal or standard Gaussian. So let us expand a little bit on this assumption here. So what does C imply? Implies that alpha t evolves over time according to a fixed or or a learnable schedule such that the distribution of the final latent pxt is a standard Gaussian. What the implications see? So what I have said is that we usually keep it fixed. I have added this learnable as well. We will see some variations of this. What do we mean by learnable? Okay, but for the moment we can think of them as something fixed. Okay, so we will come to that in detail later on. So so with this, our HVAE1 that I wrote before, hence HVAE1 becomes P x0 to t P xt product of t equal 1 to t P theta x t minus 1 xt, where P of xt is normal of xt. So if you recall, the HVAE1 we had, and in HVAE1 we had written in terms of x0 and z1 to t, but remember that z's were changed to x, so hence now we write everything combined x0 to t. So this includes x0 and all the z's as well, and hence this simplifies the notation here. But what we are asking from assumption C, what assumption C is telling us is that make sure that your distribution for the last time step is a standard normal distribution, okay, with zero mean and identity as variance. Okay, so we have these gradual transition from VAE to hierarchical VAE, Markovian VAE, and then we had these modeling assumptions now, and with this we can summarize very quickly what is our plan. Okay, so all the assumptions that we have, okay, so the assumptions in this case A, B, C, all collectively what it tells us that steady noisification of an input image over time we progressively corrupt. Basically it means that we progressively corrupt an image. Okay, this is what we do, because if you remember, we start from x0, right? So we start from x0 and we end up at xt. So basically what we are saying is that a real image is transformed in a way via those linear Gaussian transforms, such that the final image becomes a completely noisy image with a distribution from standard normal. Okay, so basically it becomes a pure Gaussian noise. Okay, so we progressively corrupt an image by adding Gaussian noise until it eventually becomes completely identical to pure Gaussian noise. This is what is going to happen. Okay, Gaussian is usually a standard distribution usually we take because of some of the regions, not just here, in many problems you prefer using Gaussian, because if the data size is large enough, then most distributions tend to be Gaussian. Okay, so if you collect enough samples, then essentially most data starts behaving like a bell curve. Okay, that's the implication of CLT, central limit theorem. So in a big data environment, let us say I have a lot of images and so on, then it will be, if the data is large enough, it will be approximated very well by Gaussian. Not just one Gaussian, you can combine them to create very complicated one. Okay, so that's why you will see Gaussians are used a lot in a big data environment, because in a big data environment, distribution will very likely follow Gaussian at some point. Yeah, Gaussian essentially tells you that extreme events are rare, average events are more, and this is very likely in real world, because extreme events are not rare, then they are common. Okay, there is a yeah. So it is very natural that something that is extreme will be less frequent. That's why we call it extreme. Something that is common. So many data will essentially follow this only. If I pick only 2 students, then it will be tallest or smallest. But if I pick many students, then very few will be extreme, very tall and very small, and most will follow, will have a peak. So there is an intuition behind Gaussian. Okay, why we model it via Gaussian. Okay, so this is the idea we are developing, that given an input image, we perturb it, we inject some noises, but we have to do it gradually in a way that variance is not introduced too much. Okay, so do it step by step, and then get to the pure noise, and then the most interesting part is the backward process, where from noise you are supposed to learn the original image. Okay, so and there a neural network will help there. Okay, so which kind of denoising I am supposed to do, starting from the pure noise, because that you are supposed to learn. How much noise I am supposed to decrease, remove, to go to xt minus 1, xt minus 2, and so on, but with also having a reference that I know the noise that was injected in the forward process. Okay, so I know the fact that I added some noise in the forward process, and now I'm learning that denoising process. So the noise that I added to get image at that stage, do I know how to denoise? Okay, so there is a lot of detail you will see here. I mean, there is a lot of calculations going on, even though the basic idea is simple, but to make things work. Huh? Yeah, exactly. I mean, the basic idea is that, but the only thing is, like, how will you do that, right? I mean, it's not, I mean, you have to formulate things in a way that you can compute it, right? So okay, so that's the whole point. Like, in this course we go into as much detail as is needed, so a research student can actually understand and start proposing their own ideas. So that's the point here. So so that's the idea here, the basic idea. And now I'm wondering whether we should do the picture again, because the picture remains the same, that forward and reverse thing. So I'm trying to kind of skip that. It's just that instead of Z, now I'm using X, so it's not needed anymore. Okay. So in variational diffusion model, so with these assumptions that we have A, B, C, we call this class as like variational diffusion model. Okay, so in variational diffusion model, or sometimes I will write this as VDM, we are only interested in learning conditionals p theta xt minus 1 xt, so that we can simulate new data. So we are interested in basically learning the denoising part. So given an xt, so this is a backward process. So given an xt, how to learn this denoising to get to lesser noisy image. Okay, so that is going to be our key step. Okay, in this. And assuming that we learn all this, then after optimizing VDM, basically after learning how to denoise, then sampling is very easy. Okay. So sampling process involves, so this is the generation part. So sampling process involves sampling from pxt plus iteratively running denoising steps. So what you have said is just now written down in the notes. Okay, so okay. So basically we run this p theta xt minus 1 xt for t steps to generate a novel x node. So we can now derive an elbow with this for VDM. Okay, so basically the steps will be similar to the hierarchical VAE. So like any HVAE, VDM can be optimized by maximizing the elbow. So this is log of Px is log of P of 0 to t and dx 1 to t. So is this we start from the same step that we did for hierarchical VAE. We start with the log. We are trying to marginalize. Remember that we are marginalizing over the latent, which starts from 1 to t, and x0 is the original. Okay, so this again we just do this very quickly with this new notations. So this is p of x 0 to t, q of x 1 to t, x naught, and we are doing the importance sampling again. Importance sampling, right? So and then as usual we write this as expectation over q x 1 to t x naught and p 0 to t divided by q x 1 to t x naught. So this is again a definition of expectation. And then we will create a lower bound by applying the Jensen's like we did before. So this is greater than equal to expectation of q x1 to t x naught log of p x0 to t divided by q x1 to t x naught. So this is our Jensen's. Okay, so and we can substitute the definition of px0 that we wrote. I guess we wrote it here. So with that we substitute. So expectation of q x1 to t x naught is log pxt product of p theta xt minus 1 xt t equal 1 to t divided by product of 1 to t q xt So we have just substituted the definitions for p, the numerator, and the denominator. Okay, there's nothing much has happened here, and we can pull out x0 x1 from here, and we will make this product go from 2 to t. Okay, so that will be the next step. Right. So I just took out few terms. Okay. So in the numerator I took out x0 x1 and then increase this from 2 to here, and then this also should be no, here we decrease so we took the last term from here, so which was xt minus 1, and we go on only on to t minus 1 now. Okay, so that's the okay. So with this yeah, so here we have 2 to t, that's fine. So 2 to t because the first term we took out, and pxt was already there, that's fine. And then we changed to 2, and here pxt px naught p theta x naught x1 and t equals 1 to. Okay, so what we can do is that we can shift the arguments. What I have done next is that we shift t and adjust the t. So I increase the t, but then in the product I decrease it, so that I will kind of put them together. That's the plan. So indexing, for the numerator also, for t I want to start from 1 to t minus 1, and then inside I will adjust that. So that's what I do as a next step. So this is divided by xt xt minus 1 and product of t equals 1 to t minus 1 q xt xt minus 1. Okay, so the only change I did is that I decreased the t indexing by 1, and then here I increased by 1. Okay, so the idea here is that these indexings are same, so hence I can kind of combine them. Okay, so that's what we do in the next step. All right. So as I said, we have split the log. So log of this divided by this, and then log of this product and this indexing are same, so we combine them. So this log, the combined thing is here. Okay. Okay, and we will split this log further. That's the plan. So this will be expectation of q of 1 to t x naught log of p theta x naught x1 plus expectation of q of I mean, I should have expanded a little bit. Okay, I think I will expand it further here. So here, this is expectation of q x1 to t x naught and log of xt divided by xt given xt minus 1 and plus expectation of q x 1 to t x naught t equal 1 to t minus 1 log of p theta xt given t minus 1 divided by xt xt minus 1. So what is it here, right? 1 to t x naught. So we took this quantity, which we see here, log of this, and this quantity xt by q xt xt minus 1 is here, and the third quantity is the same as before. In the next step, we will take the summation out. So yeah, that's it. So let us do step by step so that we keep track of everything. Now this is equal to log of p theta x naught x1 expectation of q of log of txt divided by plus sum of log of p theta xt plus 1 divided by okay. So this is like the sub thing here. Okay. So as I said, the only change happened was sum is taken out, I believe. Nothing else changed here. All right. So expectation of q of x1 x0. So why am I doing that? Because here I'm saying that I'm computing expectation of x1 to t given x0, but when I look at these terms, then only terms here are x0 and x1. So no need of those terms which are not 0 or 1 here. So we will hence compute expectation because only 1 matters and x0 matters because those are the only ones that show up. So hence we simplify this to this. So same thing I did for the second term here because I looked into this term and I saw that there is xt minus 1. So no business for other guys to be here. So we just take xt minus 1, xt, that's the only thing needed, and x0. So this now reduces to this. Okay, and then let us look into the third term. What are the things we are going to drop? Now with the same idea, we know that only terms that are relevant is xt, t plus 1 and t minus 1. So we will keep only those guys here in the third term. So I did the same thing as I said, just keep those t minus 1, t and t plus 1 terms. Okay, so this derivation, it's good to keep some of the steps. Believe is okay. So let us say that this is VDM4. Okay, and the next step is VDM5. We may refer one of these at some point, and then this is VDM6, and then the final one that we wrote. Let us say this is VDM7. I'm missing the 1, 2, 3, but that's okay. VDM. Those were the previous steps, but it's fine. When it's needed, I will rewrite. So this is our VDM7. Now what we will do is that we will look into these individual terms. Okay, and our goal obviously is to have a computational routine where we can develop an algorithm. So we will basically look into VDM7, the equation VDM7, and see see how we can simplify this further. So let us look into term by term. So let us look into the term this guy first. Okay, so I have a color chalk maybe. So let us look into this term first, and let's see what we can do about that. So look at so the proposal is that this could be written as a product, in the sense that this is okay. So the computing expectation over the joint t minus 1 t conditioned on x naught will be same as the product of t minus 1 x naught and t minus 1, and this is the consequence of the Markovian, which we could understand this as follows. So consider the graph, and this is x naught, t minus 1. So this is how we can see how they may be kind of related to each other. So so if we compute the joint distribution for this guy, so this we can write this as q xt from xt minus 1 So we can write like this, looking at the, because xt can only depend on xt minus 1, and xt minus 1 can at best depend on x naught. So this is what is relevant here, and hence if I compute an expectation of this, then it does break into that. Okay, so this implies that expectation of q of xt minus 1 xt x naught is, so I can write this guy first so that it matches that. Okay, so this makes sense. Okay, we can compute expectations like this. Okay, so also we are assuming the fact that they are independent. So basically xt minus 1 given x naught and xt given xt minus 1, they are independent. So hence the product of the expectation of the product is product of the expectations. So we have used these two arguments here. So this gives us a way to break this expectation into these two parts. Okay, that's the one thing. Now similarly we can look into the last term, third term. Okay, where we wonder whether we can also split this into some smaller products.